In chemostratigraphic studies, one needs to look at the different isotopes and salient points. I am not going to cover each and every isotope. Let us look at a few of them. Hydrogen isotopes, they are little used in chemostratigraphy. The deuterium has been used to define the Holocene GSSP. Base of Holocene has a significant change in the deuterium value, indicating significant warming. If there is a change in deuterium value that can indicate significant warming, Holocene is a time of warming. The glacial event was going away and warming started, and it is indicated by the change in the deuterium values. Carbon isotopes, there has been indiscriminate use of neoproterozoic rocks carbon isotopes, and this has been called as a blind dating, and this sometimes has given wrong results. Carbon isotope studies can comment on the oceanic anoxic environments, that means oxygen deficient environment in the deep water. OAEs generated due to rapid global warming due to volcanic degassing of CO2. 9 major OAEs are known, oldest in Jurassic, 7 in the Cretaceous and 1 in the Cenozoic. OAE implies a very high burial rate of marine organic carbon 12C, resulting in an increase or spike in del 13C value in the marine and the atmospheric carbon. So, for different isotopes, detailed discussion is available, and the interested student can go through this paper, which is a review article. Del 15N is useful when biostratigraphy is of limited use. Oxygen isotope chemostratigraphy is the backbone of the Mesozoic and Cenozoic stratigraphic correlations of marine sediments. Del 18O is usually measured from the benthic forams. So, not just the rock samples or the sediments, but from the tests of the fossils, the isotopic studies can be done. Del 13C can be measured on carbonates and organic matters, including black shells. It is more widely used on carbonate since it has more resilience in post-depositional alterations. Sulfur isotopes have been used mainly for neoproterozoic and phanerozoic isotope chemostratigraphy. Calcium and Ba isotopes are non-traditional stable isotopes, so more works are required to use them profusely on chemostratigraphic aspects. LIMG, Ca, MOCR, FeCu and Zn and Ac still to explore in terms of isotopic stratigraphy. Neoproterozoic calcium isotopes can probably comment on the oceanic calcium isotopic composition. During the Archean Proterozoic and Neoproterozoic time, it was a ferruginous ocean. Later on, the ferruginous ocean changed to a different geochemistry. MO concentration in the black shell and the isotopic composition indicate the evolution of the redox condition in the ocean. These are some of the end conclusions, not getting into the detail. There are 3 oxygenation events at 2.65 billion year, 2.5 billion year and 550 million year. 2.5 billion year is the Archean Proterozoic boundary, and 550 million year is the Precambrian Cambrian boundary. A euxinic condition prevailed from 1.8 to 1 billion year back. Euxinic condition may also presently prevail in the deep ocean. We will see some information about the strontium isotopes and the oxygen isotopes. Strontium is chemically similar with calcium. However, when we say that they are chemically similar, it does not mean that the ionic radius of Sr plus 2 and that of Ca plus 2 are exactly the same. In case of Sr plus 2, the ionic radius is approximately 1.35 to 1.45 angstrom, whereas for Ca plus 2 the ionic radius is around 1.32 to 1.37 angstrom. This means that the minimum one, ionic radius of Ca plus 2, the maximum for Sr plus 2 do not match. However, there is a common range where the ionic radius of Sr plus 2 and Ca plus 2 can be the same. Cumulatively, strontium is chemically similar to calcium. That means the strontium is found in small quantities in the limestones. In this place of Ca, some Sr might be there. There are 2 common isotopes of strontium, 86 Sr and 87 Sr. And if we study the Phanerozoic limestones, we can find out how the ratio between the two isotopes, that is 87 Sr by 86 Sr, has varied within the Phanerozoic span. These limestones are mostly found in the shallow sea. So, what we find in terms of this ratio is talking about how the sea water's isotopic concentration changed with time. And in this way, from 600 million year back to 0 million year, the 87 Sr by 86 Sr ratio has been plotted. The different geological times are represented here. Interestingly, by comparing, now if I get some 86 Sr divided by 87 Sr, but note here the ratio is 87 Sr by 86 Sr. Anyway, if we know this ratio, then from the calcite samples we can find out the age of the limestone. But there is a problem. It is not that a specific magnitude of the ratio 87 Sr by 86 Sr happened only once in the geological span. I just took this point, and if I move geologically time scale wise towards the younging direction, I am finding that the same magnitude came so many times. Therefore, one has to be alert in applying this simplistic statement. Now, if we know that the calcite sample is between Jurassic to Cretaceous age, in that case, knowing a specific value, we may be able to point out two possible ages. Another point, in the Neoproterozoic seawater, the 87 Sr by 86 Sr that was obtained, with progressive time we do get the lowest 87 Sr by 86 Sr ratio within the Jurassic period. So, the ancient sea waters 87 Sr by 86 Sr fluctuated significantly. There are many crests and there are many troughs. While picking up the carbonate samples, we have to be very alert that these carbonates should not subsequently be recrystallized. If they got recrystallized, then these carbonates are to be avoided in finding out the 87 Sr by 86 Sr ratio. Many organisms make shells of aragonite, but these cannot be used because aragonite recrystallizes to calcite through time. If we find aragonite crystals in organism's shell, this one cannot be applied or cannot be used to study 87 Sr by 86 Sr. So, what kind of shells, what kinds of organisms to be chosen? Organisms which precipitate calcite in their shells or in skeletons can be used, and that must be free from alteration. So, this one cannot be considered, and what can be considered is organisms with calcite as either shells or bones. Let us look at the oxygen isotopes. The commonest isotope of oxygen is 16O, but about 0.2% of naturally occurring oxygen is 18O, the heavy oxygen, and both of them are stable isotopes. They do not undergo radioactive decay. Interestingly, 16O, the lighter isotope, preferentially evaporates into the atmosphere. The process is called isotopic fractionation. This means when water is evaporated, preferentially 16O is released as vapor. Atmospheric water contains more 16O. And during the glacial period, a high proportion of the globe's water is held in the ice cap. So, here what are we talking about? In the geological context, we can link this with the global cooling. Now, these ice caps are fed by the water from the atmosphere in the form of snow. As a consequence, during glacial periods, there is more low 18O ice. Ice gets low 18O content, and the oceans are relatively rich in 18O. This variation of the 18O divided by 16O in the ocean water with temperature provides the basis of oxygen isotope stratigraphy. Students have to remember what is the basic principle behind the oxygen isotope stratigraphy, and here is the answer. The oxygen isotope ratio is actually represented in terms of delta 18O, and negative value of delta 18O means depletion of 18O, and a positive value means it is enriched in 18O. From where we find out the oxygen isotopic ratios, we use the benthic forams of Mesozoic and Cenozoic strata, and on the brachiopods and mollusks of Paleozoic rocks. Seal and others in 2015 made an interesting compilation of various geochemical profiles: del 13C, del 18O, 87 Sr divided by 86 Sr, del 34S, del 34S again, del 44 by 40 Ca oceanic redox state number of animal genera. These have been plotted in the geological time scale, and here we are seeing a part of it, only the Paleozoic portion. Each of these curves may not come from always a single author, but a portion was derived by some author, another portion was another author. So, compilations have also been made in these graphs, and here is the sea level in the past. Is there any correlation between the increase in del 13C and del 18O, del 13C and 87SR by 86SR, del 13C and anything, and del 34S, or del 18O and del 34S? Let us see with time what has happened. We are finding many spikes, BAC, SHIC, ROEC and SNIC. These are the negative excursions of carbon isotopes, because from the standard 0 line they have all gone to the left, and ZHUC, MIC, SPIC, GIC and also up HIC indicate positive excursion of the carbon isotopes. The red lines indicate mass extinctions. Here 3 of them are shown: the Ordovician mass extinction, the Devonian mass extinction and the Permian mass extinction. Then the glaciation periods have been plotted by these lines. This is 1, this is 2nd and this is 3rd. One observation is that when the first glaciation happened, it was followed by Ordovician mass extinction. There was no immediate follow up between Devonian mass extinction and glaciation, and in fact here glaciation has happened much earlier and much later Permian mass extinction happened. So, it may be possible that this glaciation directly had no effect on the Permian mass extinction. Do you observe that when there is mass extinction, there is a drastic fall of del 13C value? From here it goes down and here it falls, and from here step it goes down in this direction. So, we can say from this compiled chart that del 13C value reduced when mass extinction happened. The mass extinction is also indicated by the number of animal genera. We can see this curve, it falls down here, here some fall is noted and here again a fall is noted. So, the extinction has affected the number of animal genera. Certain curves are insensitive of the mass extinction. There are certain isotopic parameters which are independent of the mass extinction. For example, here the del 34S pattern shows a bell geometry. Isotopic ratios seem to be independent of the events on the earth. For example, the glaciation that happened here, and if I follow del 34S curve, it does not go down. Here, at least in this portion, it is bell shaped, looks like it was not affected by the glaciation. Whereas in this case 87SR by 86SR fell down during the post glacial time. What happens in case of the del 13C values? This is the place the glaciation event is shown by the colored line and the mass extinction by the red line. Here is a fall, but now this becomes difficult to say that this fall is of del 13C due to glaciation event or due to mass extinction, because they have superposed. If I observe here that there is indeed a fall of del 13C value when the glaciation event was persisting, and what happens in this place? If I take this as the prevailing del 30C value, some fall is recorded during the glaciation period. During glaciation, the animals might reduce in number. That can be another reason. Just like the mass extinction situation, del 13C falls either strongly or gently during the glaciation event. The 87SR by 86SR ratio starts falling much before the glaciation period, and after glaciation and mass extinction got over, it moved up. Then again it went down, and while closer to the mass extinction time it got reduced. After mass extinction it was moving up, it started falling gently in the glaciation period. It may not always be possible to link the isotope with events. Suppose we try to link del 44 by 40 Ca and the glaciation period. At least in this position the curve is not giving a spike, but when this glaciation was happening, actually much before that the curve was moving up and then it started falling down. So, making a definite sentence not always is possible. This figure's caption I have presented here. so that students can read and correlate. What I was only referring in terms of the abbreviations BAC, SHIC and others, you can find out the full forms here. These names and the full forms I will not ask you in the exam. Now that we have seen the Paleozoic world and the isotopes, let us see the Mesozoic and the Cenozoic time and how the curves behaved. Here we are getting the Jurassic Triassic mass extinction and the Cretaceous mass extinction. This is the time beyond which we do not see the dinosaurs, they got extinct. The sea level fluctuation is shown by this curve. Again, in case of a mass extinction, we find a sharp drop in the del 13C. Same thing is observed over there. So, this looks to be a consistent feature that del 13C falls when there is a mass extinction. So, this statement what we made for the Paleozoic world is also true for the Mesozoic and the Cenozoic world. LPTM is a late Paleocene thermal maximum, which is shown here. At LPTM, we find a rise of the del 34S and here a fall in the del 13C. This thermal maximum probably led to some extinction, and that is why del 13C fell down, but it was not as massive mass extinction as the Cretaceous one. OAE is the oceanic anoxic environment. Here is one of the OAE, the second one and the third one, and three of them happened within the Mesozoic time. We observe that the extinctions are almost superposed with a fall in the sea level. Why so? Is there any link can be thought about? The two glacial events are demonstrated here. If we find the corresponding time, what happened in the del 13C, we do not see a significant drop in del 13C values. Much earlier I have said that when glaciation happens, the sea level falls because water becomes ice. That can be checked here. As we track this green line, we find here there is a fall in sea level. Here also a fall in sea level is observed. But in this glaciation, we find actually a rise in sea level. So, these are some of the problems. The statements that we are making that during the glacial time the sea level falls are the general statements. Actual detail can be cross checked. A detailed caption and this figure is presented here so that students can read. Let us look at the different isotopes and their uses in stratigraphy. To know how the carbon isotopes can be used on the sedimentary sequences, we need a prior knowledge on the secular variation of marine carbon isotopes. This is essential. Let us look at how the del 13C has varied. In the geological past, we do not have record of del 13C for the Hadean and for the Paleoarchean time. From Paleoarchean onward, we have the del 13C record. Here, the glacial event is marked by faint blue color once, twice and thrice, and at least in case of the first glaciation that has happened in the Mesoarchean, we do not see significant change in the del 13C value. Del 13C reduces when it was crossing the glaciation period. In the time of GOE, that means the Great Oxidation Event shown here, we find there is a spike of del 13C value, and when the Great Oxidation Event stopped, it also fell down. There were several fluctuations of del 13C values. Then in the Paleoproterozoic, for most of its part, the value was almost similar, and then there are a lot of ups and downs in the curve. In the glaciation period, there is significant fall of del 13C value. The del 13C of carbonates is more widely used in chemostratigraphy except in carbonate pore successions characterized by black shells. Del 13C minima follow the main extinction events. Post-depositional alteration of carbonate rocks under study may radically alter the del 13C value. So, petrographic study of rocks are required to find out if any alteration happened in rocks, and in case such alterations happened, then we should avoid those rocks in this study. In the Paleoproterozoic, we find a carbon positive anomaly, and this is shown in this place. This is the carbon positive anomaly. Many studies have reported carbon isotope variations in the Neoproterozoic carbonate rocks and linked them with the perturbation of the global carbon cycle. Let us look at the nitrogen isotopes. The utility of nitrogen isotope for stratigraphic correlation or study of the evolution of atmospheric chemistry remains ambiguous. However, a few of the authors have found promising tool. The use of del 15N profile is perhaps a promising chemostratigraphic correlation tool, especially where biostratigraphy is of limited use. Denitrification process by which nitrate and nitrite are reduced to nitrogen gas is an important part of the global nitrogen cycle in the modern ocean. Oxygen isotopes. Oxygen isotope chemostratigraphy forms the backbone of Meso and Cenozoic stratigraphic correlations of the marine sediments. In the past, from -8 parts per thousand to 0 part per thousand, that means VPDB in the Phanerozoic has happened with the oxygen isotope. That means not always the delta value of oxygen isotope remained positive in the Earth's history. For very old rocks and sediments, oxygen isotope cannot be used because of the absence of the calcified metazoans in the Precambrian. Except for the area current, it makes it very difficult to use del 18O analysis for the whole rock samples of the Precambrian successions. Let us take sulfur isotopes. Sulfur isotopes are largely used in the Neoproterozoic and Phanerozoic isotope chemostratigraphy. A secular variation in curve of del 34S was found with the evaporites starting from 1 billion year to the present time. Calcium and boron isotopes. Recent technological advances in the analysis of some of the non-traditional stable isotopes with MC, ICP, MS. What are those elements that are now studied in detail? LIMG, CAMO, CR, FeCu, Zn and AC. They have opened up new avenues and still work is going on. Calcium isotope stratigraphy is an additional tool to correlate the post-glacial Neoproterozoic carbonate successions. But note that the Neoproterozoic calcium isotopic record is still far from complete. Then there are different other interpretations of the isotope. Chromium and molybdenum isotopes. The study of Fe, Cr and MO isotopes has provided important insights into the question of surface ocean oxygenation. Delta 53 Cr can give us an idea about the oxygenation history of the Earth's atmosphere when the banded iron formations were picked up. Chromium isotopes in the carbonates can be useful as a tracers for the climatic changes. The chromium and the carbon isotopes curves in the carbonates are virtually parallel, and this has been recorded as early as 2011. The molybdenum concentration in the black shell and its isotopic composition have been used to assess the evolution of the redox state of the ocean. So, in that perspective, molybdenum becomes important. Strontium and neodymium isotopes. Fluctuation of 87 SR by 86 SR ratios are independent of those of del 13C. We do not see a pattern of fluctuation between 87 SR divided by 86 SR and del 13C. They are independent, but they can simultaneously be utilized to understand, to decode the high resolution stratigraphy. 87 SR by 86 SR secular variation has been better known from the Phanerozoic rocks. The high 87 SR by 86 SR ratios can reflect enhanced orogenesis, that means mountain building process. When it happens, the 87 SR divided by 86 SR ratio might go high, and when the 87 SR by 86 SR ratio is low, that can characterize periods of continental breakup and enhance hydrothermal activity. Here in this curve, we are finding high 87 SR by 86 SR ratio in the Mesoproterozoic. Are there any evidences of orogeny of this time? We are finding 87 SR divided by 86 SR ratio to be very low at this point, which is a time of the Paleoproterozoic. Is there any time of continental breakup that took place here? We need to look at other charts that the geologists have compiled and find out whether any continental breakups. The problem is very old tectonics of the earth is not well understood. So, once we are already in the Proterozoic domain, it becomes difficult to interpret. Supercontinental Rodinia got formed in the Neoproterozoic and the top of Mesoproterozoic, and Nuna developed in the Paleoproterozoic, but here In case of Nuna, check with the SR by SR ratio, we find only a gentle increase with time. And in case of Rodinia continent formation, here we find for a long time SR by SR ratio was same, did not change much, then it got a peak but started falling when the Rodinia supercontinent was already there. So 100% link with events are not made, but the study is ongoing. Neodymium isotopes have little use in stratigraphic tool, although a global average epsilon neodymium curve for the ocean since 800 million years has been constructed. An average epsilon ND value decreased remarkably in the time interval of 700 to 550 million years, and the number ranged from -5 to -15. We do not see a ready explanation of event that led to such a situation. Elemental chemostratigraphy Hg, Mo and V seem to be elements of particular interest. Hg or mercury tends to concentrate in sediments deposited right after the major glacial events as a result of leaching from the volcanogenic mercury from the land surface and accumulation along argillaceous sediments. Let us look at the major glacial events. Here we have got some glacial events. So, these are the time when, as per that statement, the mercury concentration in the sediment should increase in the argillaceous one. Hg can be used as a proxy for the volcanic activity and CO2 buildup during snowball events in the Neoproterozoic cap carbonates. Molybdenum concentration increases to Phanerozoic values in black shells. Same pattern has been noted for the vanadium concentration within the black shells. A request to students, black shell I have been referring many times in today's lecture. Find out which elements are enriched in black shells. Molybdenum and vanadium chemostratigraphy may be useful in the investigation of the redox state of the deep ocean water, and their ratios such as I divided by Ca ratios can be used as a paleoredox condition to verify the surface ocean oxygenation. Now, let us look at geological time wise what are the temporal trends and signatures of the Earth's chemicals. The Precambrian comprises 82% of the geological evolution of the Earth, and this is the time when the sedimentary rocks contain only the small, mostly microscopic and relatively scarce fossils. Fossils were very little, life was in a very primitive form, and their preservation potential was also very poor. The oldest Archean microfossil occurs in 3465 million years back within the charts. Photosynthetic organisms were extant, that means they were present by 3.7 billion years. We have scarce amount of delta 13C data, but that values are close to 0 parts per thousand VPDB, suggesting a biomass in the ocean similar to the modern day biosphere. This is important. Biomass in the ocean similar to the modern day biosphere was developed, and from this line actually geoscientists think that the early origin of life and rapid development of a relatively large biomass in the early oceans took place. Life first developed in the ocean, not on the land. For the first 2 billion years, the oxygen concentration in the atmosphere was very little. That was a problem to support life. The great oxidation event GOE, students must remember the range 2.4 to 2.2 billion years is a remarkable event on the earth. Paleoproterozoic measurement of well preserved, even metamorphosed carbonates have provided valuable insights on the biogeochemical cycle of carbon in the geological past from the Paleoproterozoic. Studies of Proterozoic rocks reveals time intervals at the beginning and the end of the Proterozoic with highly positive carbon isotope values. Carbon isotope value became highly positive. The delta 13C chemostratigraphic curve for marine carbonate starting at 2.5 billion years shows a widespread positive delta 13C in the Paleoproterozoic. Let us look at the graph. This is delta 13C and this is the Paleoproterozoic. So, if we go within this portion, at least here we find there is a strong positive delta 13C, and this strong positive delta 13C indicates proliferation of the organisms which was supported by the presence of great oxygenation event here. So, since the great oxygenation event took place, life persisted, but then there is a sharp drop within the Paleoproterozoic itself. The unprecedented positive delta 13C anomaly, and they are known as the Lomagundi or Jatulian events. The duration of the Lomagundi phenomenon is still a matter of debate. Lomagundi took place in the Paleoproterozoic, remarkable jump in delta 13C values. The Lomagundi excursion is now also found from South America and the Indian continent, with recent studies coming up. For example, Maheshwari and other in 2010 found that the Lomagundi excursion happened in the shallow water deposits of Aravalli supergroup in India. Let's look at the Mesoproterozoic. The carbon isotope chemostratigraphic studies in the late Paleoproterozoic 1.8 to 1.6 billion years showed that delta 13C value was mainly negative here and increased slowly, reaching a level of 0. I am requesting students to look at this graph and correlate the sentences, as I have done with some of the sentences. The late Paleoproterozoic and Mesoproterozoic oceans were interesting because euxinic conditions dominated for almost 1 billion years. In this euxinic condition, black shells were deposited, and this was a place, this rock was a site of concentration of molybdenum, vanadium and other elements. Let us look at the Neoproterozoic. In the Neoproterozoic, the delta 13C secular variation curve shows strong positive and negative excursions. Delta 13C seems to be very sensitive, and it shows both positive and negative excursions. Within the Neoproterozoic, the cryogenian time between 750 to 635 million years is a time of extreme climate changes. Remember that cryogenian is a part of Neoproterozoic and where the extreme climate changes have been worked out. Let us look at the Paleozoic world. We now believe unequivocally that the Ediacara developed in Paleozoic. So, Paleozoic's beginning can be called as the Ediacaran period, and the Precambrian-Cambrian transition is characterized by a profound negative delta 13C. Precambrian-Cambrian transition happened around 550 million years back, where the delta 13C fell down significantly. Here is the delta 13C curve, and upward is the Cambrian. A large and global positive delta 13C excursion for the upper Cambrian carbonates has been reported from several continents. Let us look at the Mesozoic. The anomalous mercury level caused by the catastrophic Siberian trap volcanic eruption was the major reason for the mass extinction in the Permian Triassic boundary. This Permian Triassic boundary has been also called as the Great Dying. An asteroid impact is an alternate explanation for the PTB mass extinction. Cretaceous marine sediments in Europe are mainly comprised of white limestones and chalk. The Cretaceous has come from the Latin word for chalk. Black shells again formed in the Mesozoic and under an oceanic anoxic event, or the OAE. The ultimate trigger of the anoxic environment could be the sea level rise. If the sea level rises up, then there exists a deep sea condition somewhere where anoxic condition can prevail and fine grained sedimentary deposits in terms of shell can be produced with or without the element arsenic, with or without the mineral pyrite and also arsenopyrite. Let us look at the Cenozoic. An anomalous amount of iridium of 3000 ppt in a 1 cm thick clay layer within a sequence of pelagic limestone at Gubbio in Italy was later found in several localities worldwide. This iridium concentration is a matter of great interest. And here we are talking about the Cretaceous Tertiary boundary. From the beginning of the Cenozoic until just the end of the Eocene, there was a warmer climate and a greenhouse world has been proposed to explain the scenario. Remember the term greenhouse world, and it has been used from the beginning of Cenozoic just after the end of the Eocene Oligocene boundary. Isotope stratigraphy is growing rapidly, and it has benefited from recent technological developments and the analytical facilities, opening new ventures to explore non-traditional stable isotopes such as Li, Mg, Ca, Cr, Mo, Fe, Cu, Zn, Ac and Cl will add in future more geological knowledge. Amongst the traditional stable isotopes, carbon, oxygen and sulfur, remember these three have been by far the most used within the chemostratigraphic realm.